Okay. All right, so let's start the talk then. We're happy to have Rafael Dupre talking about nuclear effects and mapping of them in 3 dimensions. And I think in the interest of fairness, please stick to 45 minutes, even though you understand there's no solid cutoff.
Don't worry, I'll more likely be shorter than longer.
Oh, really? Well, don't worry.
Actually, the initial topic was more nuclear GPDs, and I made it a little bit wider and extended to TMDs because there was a lot of discussion on that, and also because it was a bit short. So I think those are related topics, and they have different issues, but all of this can be linked. So let's start with the very basics of how to describe a nuclei. And being in hadronic physics, we have to not forget that the basic picture of the nuclei is made of protons and neutrons. And this picture works pretty well. You can describe a lot of light nuclei exactly with this. You can even do some electron scattering. You have here form factor of helium up to relatively reasonable Q square, and all of this can be described just with protons and neutrons, and just if you want to access the partonic side, you just say, okay, I look at the partons in the protons and neutrons and I put them together, and it works somewhat. So that's the first level, and then eventually you reach a point where it starts not working anymore, and those are the nuclear effects we know. You see them here. We talk a lot about shadowing and EMC effect. I want to remind people of the anti-shadowing, which has didn't get much love in the past time by either theorists or experimentalists, but I think it's something that is very worth thinking about, and it actually falls right in a place where JLab, for example, measure very well. So there is no reason not to look into these things. And there was plenty of models to try to describe this, and that was very prolific for a long time. And eventually, with time, a lot of those models failed. So the first idea was, since where they explained the nucleon-nucleon interaction with pion exchange, you said, okay, let's put some pions in the nuclei and things like that. And people were starting to look at deconfined or clusters where you would pack 6, 9, 12 quarks, valence quarks. And eventually, these kind of models, what they were doing more or less was, in order to get this suppression on the U quark, what they would do is that they would transfer a lot of the momentum to some C quarks. And if you do that, what happens is that when you do the Rayleigh ratio of the nuclei of the deuterium, the C quarks should shoot up. And so you go in an X range slightly lower, and you're looking for a big increase. And well, data didn't see that, so that killed a lot of models when that was measured. So now there are a lot of other ideas. Did you change the size of the nucleon, leading to maybe some Q square change, or do you just remove energy from the nucleons with binding, and then you get X rescaling? Because one of the interesting facts with all this EMC effect and the start of the shadowing is that if you just shift the PDFs in X or Q square, since thanks to DGLAP it's more or less the same, you eventually get a shape that is pretty similar to this one. So that seemed like something very reasonable. I think the main issue with that is that the physics actually behind shifting X or Q square is very different. What you're putting in there is very different. Since this is a workshop that goes toward EIC, I wanted to show also a little bit more on shadowing, and we hear a lot, I heard a lot about people that have models, and I wanted, from an experimentalist point of view, remind that we actually have very little data below x of 10 to the -2. When you look at NPDF's fits, what you see is that we heard about this yesterday. You apply a Q-square cut that is pretty tough, and you actually lose most of those data. And the truth is, we don't really know so well what's going on there. And here I took this figure, so it's a little bit old, but I don't think there is any new data in there. But that just shows the spread of a lot of theoretical models. And what we see is that the suppression could go from anywhere from 20 to 50%. If you believe this, and that shows that actually shadowing that some people would argue is more or less understood. We have some idea of what it comes from multiple scattering and ideas like that, is actually not that well understood. And having data there would be very nice, and that would be very nice just in terms of NPDFs, but I would argue it's actually even nicer if you get it in terms of GPDs or TMDs, because now you offer an extra constraint to your models and calculation.
So this is for what? So let me clear.
Yeah, so this is less.
This is consistent with the uncertainty currently for DVCS 16.
It's not far, yeah. One of the things with nuclear PDFs that you have to be very careful about is how they translate there or at very low X, because sometimes just because of DGAP evolution, it looks like the error doesn't blow up, but actually there is no data to constrain anything. And I'm always a little bit unhappy because a lot of groups, and I think Fred didn't do that, but a lot of groups show everything down to 10 to -5, which when you're doing nuclear PDFs is a kind of a nonsense, because you have no data for like 2 orders of magnitude, and you're just extrapolating things completely.
Actually, when we did the same study for the impact on EAC, we had to give more freedom in DVCS at low X, otherwise it's like
exactly.
Function reform itself is.
And I mean, it's also something that is relatively current, but with fits is that, I mean, fits have strange behavior, but we have to keep in mind the reality behind it is that we actually have no idea what's going on. We actually, if you look at some of the more generous fits in terms of error bars, it's almost consistent with 1. So some people could almost claim that we do not have a strong evidence of just the fact that there is shadowing. So it's a pretty problematic thing. And we also heard of why this is very problematic, because if you do LHC, you go to LHC or RIC, the X you are sensitive to are actually right in this range. And so you see that, and that leads to huge initial state errors. So even though we usually present shadowing as understood in terms of we know more or less what kind of process leads to that, I would argue that in terms of it's only a qualitative understanding. The quantitative is clearly not there at this point. So the question is, where do we stand in this? And because trying to describe the nuclei just in terms of quark and gluons is just a lot of problems, and that's not relevant for every observables you try to describe. And you need to understand where is the boundary between those worlds. And so the question now is, how do we resolve between the different ways of describing the nucleus in terms of quark and gluons? As soon as you go there are plenty of models, and we don't have much. And my argument is that, yes, with EIC or anything at relatively high energy, we can measure NPDFs, but PDFs is a little bit the object of the past. Now, today, what is relevant is 3D structure functions. And for that, we should already jump for nuclear targets to this kind of analysis and say, okay, that's what is going to be the future. So let me talk rapidly a bit about GPDs. We heard a little bit before. Just to point out that the 3 dimension we actually have in a GPD, the 3 independent variables have little to do with the 3D that we imply. That's actually, I think, a little bit of an issue. Sometimes we are mixing 2 different things in there, and it's accessible through a whole series of exclusive processes, and I think we talked a little bit about that. So today we only use DVCS. I don't know of anyone doing a fit that use anything else than DVCS, but the truth is there are many other processes, and on the theoretical side we'll have to make some progress there, because when you have a 4-pi detector, you measure everything, and you should definitely use all of that. DVCS in particular has issues, and the main issue is that X is not directly measurable. So when you do measure the DVCS diagram, X gets lost in this loop, and when you measure our Compton form factors, and mainly the imaginary part, so you're measuring at a specific point in X equals psi or X equals minus psi, and with some asymmetry you can get to the real part, but then it's just integrated over X. So if you can get to the point where you measure most of those, you can get a reasonable constraint, but you really have no idea of what's the shape as a function of X. That's DVCS is not going to tell you anything about that, and that's a little bit of an issue, I'd say. Okay, so about measuring DVCS, so we always still talk about measuring DVCS, but what we measure is not DVCS. What we measure is electron production of a photon, because there are 2 processes. The other process is the beta-Hitler, where the photon is produced by the electron, and those 2 guys interfere, and it's actually a blessing, because that actually is where all those asymmetries come from. So if there was only DVCS and no other process to interfere with, this would be an impossible task. We would have a very small cross-section, a single observable cross-section, and it would be impossible to actually understand easily what's going on in there. The interference leads to a lot of asymmetries, and that's very, very nice. So today, observables that are measured are absolute cross-sections, spin asymmetries from the beam, target spin asymmetries, double spin asymmetries of the target and the beam. And you can also, when we talk about target asymmetries, you have either longitudinal or transverse being experimentally much more difficult. And finally, you have charge asymmetries, and they are the one where you replace electron with positron and giving access to all these real parts, and really they are probably the ones that give the most constraint on what the X dependence is, even though you don't really have it. That's what helps the most. And if you use all this theory, and I'll talk a bit more about it later, but just here you can see some fits. So eventually you can extract, so this is the imaginary part of H as a function of psi, t, and q square, and you get a bunch of those points, which in turn you can fit in as a function of t. And so this is what we call a local fit, because you extract the Compton form factor for every kinematics without looking at the neighbors, and then you put all of this together and you get those points which have large error bars, as you can note. So those are systematic errors correlated with the size of the model. So here it was done to be very conservative with a factor 5 on the model. You can, if you believe in so it's using the VGG model. If you believe in the model, you can shrink the error bars as much as you believe in the model. But eventually, what you see is a slope that might not seem very strong, but what you have to keep in mind is, if you want to make those points flat, what you have to do is to compensate through other Compton form factors. So you would have to put the slope of the let's say H tilde Compton form factor going up, which that's obviously problematic. So it seems that we have now many people doing fits that say that they observe that the nucleon size is shrinking with X, which actually is very obvious if you look at this, because here if you look at log psi, you have a pretty strong slope, and then it gets flatter at larger psi. So this, the data actually shows pretty well. And that, I think, is a pretty good indication that the framework works. And what you're extracting, even though it's very low Q square, T is not that small and so on, and you can talk about a lot of issues in those data. But what you see is that actually you observe what you're expecting more or less. So what happens if you go to the nuclei? So the first thing to keep in mind with the nuclei is that nuclei, you have now some kind of a control on the spin, because you have plenty of nuclei with different spins. And that actually, and I'll talk a little bit more about that, but it's actually very important. Spin 0 targets have only 2 GPDs. Proton-like targets, spin half, have 8 GPDs. So we usually hear about half of them because only half of them intervene in DVCS. But if you want a full description, this is always the double. And if you want to start to look at deuterium, for example, you have to jump to a lot more GPDs. And that can be an issue, as we've shown, because if you don't want to make assumptions about all those GPDs that you don't measure, that leads to problems. And in the nucleus, when we talked about discussing nuclear GPDs, that was also mentioned rapidly, there is actually two processes, two channels, the elastic and the quasi-elastic. I mean, they correspond to the elastic and the quasi-elastic. So in DVCS, we call them coherent and incoherent. So you see the diagram here of the coherent. So you pick up a quark from something, likely a nucleon, and at the end you actually have a full nuclei. So this is the real DVCS in principle. But you can also do this incoherent where, like in the quasi-elastic, you actually do the DVCS on a bound nucleon, which at the end you kick out of the nuclei. So that's in that case, you're more looking at the modification of the nucleon. In that case, you're really looking at your nucleus altogether. So this gives a slightly different information. And I would argue that's the very, very nice tool to look at the helium C effect. And as I pointed out, eventually to the shadowing, if you push this to EIC, because now not only do you see the modification, but you can start to localize it. And I think that's a very, very strong statement, because if you start to say, okay, for example, shadowing, you should have a much stronger effect in the center of the nucleus if you think about multiple scatterings and things like that. So the signal should be very clear and very clean for all these things. You should have a much easier way to confirm your model by looking at this in 3D. Yeah.
Sorry, it's a very naive question. Is it obvious that the real photon would be emitted by the same nucleon as the one that was hit?
You mean in this diagram?
Yeah, presumably mainly in the.
So in this diagram, yes, because all of this is relatively low energy, while this photon, what you have to keep in mind is that you always cut in to be in a deep inelastic. So, for example, even at, if you think about 6G experiments at JLab, those photons are always more than 2.5 G. So it has to be the same. You can think about some processes where you would hit, like, you would have an inversion of the two nucleons in here, but the scale of this is greater than the GV. So that would mean actually that those two guys are stuck together. So it would go back to some kind of model like 6-quark bag or stuff like that. And that's actually a point I wanted to make about the coherent, because here in this diagram I show that you pick up a nucleon, but actually this is model dependent to say you pick up a nucleon. You can actually, you're just picking up a quark inside a nucleus. There is no. The nucleon degrees of freedom are usually only involved at the model level or the calculation level. But if you just look at the principle of the reaction, you don't have to assume anything. You could, this can come from anything, and that's interesting for models that have mesons inside the nuclei, because then if you start to have lighter elements that can go here, it will show up in different kinematics, but it also possible if you have like what we were saying, two nucleons close by that would exchange their place or something like that, or exchange quarks at very short distance. That also could show up very easily, and you can identify those pretty easily because when you so this is usually used to in the plane wave inverse approximation calculations. They're using this kind of diagram, and it creates a lot of forbidden space, a lot of place where you're supposed to measure zero and have zero cross section. And so if you have things there, it might indicate other things.
Well, I was also, let me just finish on there. I mean, I was also thinking of small x limit, right? Which is probably not what you have in mind, but the small x, you can have a virtual photon split into a dipole, and then you have a pair, and the dipole will go through the nucleus, interact at will with whatever nucleon it runs into, and then it may recombine back into a photon, real photon. Then you would not have focused this picture at all. Maybe that's what you were going to say.
So my question is more about the experimental aspect of this. You put a cut of 2.5, right? You also lower this cut.
No, we don't. Okay, let me answer that. So just to come back, I mean, the picture you're describing, you see in all those vector meson projections. Exclusive vector meson. For it to recombine in the photon, I never looked at what diagrams would do that, but I would assume this is not so.
I mean, I'm not
as
saying
easy.
DVCS also has that.
Yeah, you're just saying.
It's pretty severe.
Yes.
And you have interactions with all your nucleons as many times as you want.
Yeah, you could have a coherent process like that, definitely.
right, but the small x, of course, if that's not what you have.
It's very unlikely we have an RX and things like
No, not a JLab. Yeah. Saying a small x.
Yeah,
Yes.
I mean, this would have to be looked at if it has significant contribution at the right. To go back to what you were saying, we don't really cut. What happens is that this is an indirect consequence of if you ask a high energy guy here and you detect this guy intact, you always left with a lot of energy because of the kinematics. So it's not really a cut that we apply on the energy of this guy. It's just when you apply cuts on the virtuality of this guy and you actually detect this guy, you are left only with high energy guys there.
That's it. But it applies more to the second type.
It's yeah, that it does the same. Because I mean, this is just pure kinematic. When you do those cuts, we are not really applying a cut on the energy of the photon. It just shows up, and I mean, this is linked because it's an exclusive process. So of course, here you have you are putting many GVs, and if you want to have an intact nucleon, usually you're left with a relatively small t, and so at the end, the rest of the energy has to go somewhere under the photon. So that's how it ends up.
Just experimentally, when your square root of s increase very quickly, your coherent cross-section drop, you will have not much chance to see.
So what happens with those cross-section is that it mostly dependent on t. So yeah, what is true is if you go to high t, those cross-section drops. But at low t, even at high energies, I mean, the cross-section will change, but it won't drop dramatically. So the issue, for example, with EIC is more of an issue of detection, because now you start to go look at very small t that are things that have a tendency to be very close or even stay in the beam, and that's an issue. And I'm not going to talk about it much, but there is Hermes data that was done, the first data on those kind of things, and they try to separate those two things just with the T, because they said now if you have an heavy target, you contribute more at low T, and now you're hitting an effectively lighter target, so you contribute at higher T. And when they looked at the results, they didn't see any of the expected nuclear dependencies. So that seemed to indicate that this method fails. And as I will get to very soon, you actually will at JLab do see those dependencies by detecting that and making sure that it's occurring. So detecting the end is not that is very important. I'll make the point again. So
Okay.
because
So, but
I'm
I'm sorry about
anticipating.
what you mentioned about release that they already did this, but they found no difference.
I was getting ahead of myself, so I'll talk about that. Okay, so I'm not going to talk about GLab much, just to say that these experiments are in class, semi-large acceptance spectrometer. So the challenge here is that it is an exclusive process, and usually people experimentally will measure exclusive process by missing one of the particles actually and just reconstructing it through missing mass and missing energy and so on. The issue when you do that with nuclear DVCS is that you're working with energies that are so far away. You are looking for an alpha, so here it's on the helium-4 target, so you're looking for an alpha of 7 MeV. And you have an energy of your electron that is 6 GeV, so it's 1 per mil. And what happens is that any very small error on the high energy particles, and you have no idea what's going on with the low energy ones if you start to try to reconstruct like that. So what we did is we built this small chamber. So this is actually probably bigger than the life size. It's a very small detector just placed right around the target to detect the very low energy nuclei. And we had a very forward calorimeter that was built for all those DVCS experiments you see from class. And so here is the hole for the beam. So this is a small angle because you produce those high energy photons very close to the beam line. And of course you use class for the electron. And putting all of that together, we were able to actually measure the asymmetries of the beam spin asymmetries of the helium. And as you can see, asymmetries are somewhere between 30 and 40%. So you can put that in comparison with measurement on the proton, where they are around 15–20%. So you have a doubling of those asymmetries. And here you can see the points from Hermes. And so in their case, they did helium, but they did also a bunch of other nuclei. And what happened is that they didn't see any A dependence. So you can put that on several things. First, the error bars are pretty big. So that's, of course, first issue. It could be 20, 15, 20%, or it could be, I mean, it's not incompatible with what we have either. So it's, we can't really say much with those. But also they use much heavier nuclei where they should have seen an effect and they didn't. And that's, so that was raising questions. And this increase is almost mandatory just by the factor of Z, because the beta Hitler and the DVCS cross-section don't grow in the same speed. And therefore their interference, because, so if I remember correctly, the DVCS is much smaller and it grows faster with Z. And so as the two contributions become of more similar size, the interference becomes bigger. And so that's why you get a bigger asymmetry with the helium-4. So we were very happy with that because that shows that we are really isolating this asymmetry. We cannot, since it's a bigger asymmetry, we cannot get it from any background process. It means that we are actually really extracting that. And one of the reasons we were working with helium-4 is that helium-4 is actually spin 0. And that leads to a very nice thing is that in spin 0, in DVCS, there is only one GPD that intervenes. So one quantum form factor with an imaginary and a real part. And since there is only one, and actually, if you look at how it contributes to the beam spin asymmetry, you have different contributions, and you have a contribution that goes with the imaginary part, a contribution that goes with the real part, and contribution with the sum. And when you do the fit, so here you can see the different contributions. You have the cos phi and the sin phi's contributions. So the black one, the sin phi, is the dominant one. It's the one that goes with the imaginary part. And that means you extract the imaginary part very nicely immediately. The real part comes from this alpha 2 contribution, so it's a cos contribution that is a bit more difficult to extract, and mostly because it's small. You can see all the results are consistent with 0, which is, by the way, very what was actually predicted by theory. Theory was expecting a very small contribution. But here, by opposition to what we've seen with the proton, there is no model dependence, no anything. This is just the straight extraction of the GPD. And actually, I could argue that this is the first and only model-independent extraction of GPDs to this day. Because I know of no fit of proton GPDs that don't have to make assumptions to bound some content from factor or things like that. This has no limit. You just put this formula, fit the data point, and get bounded results immediately. There is no uncertainty there. Of course, those were very first data, and the statistics is not that large, so it's not at the level where you can differentiate models. Yeah.
So the dependence obviously will come from the real part. Is that you assume that the real part is totally dominated by the Heidler in that particular expression?
I am not sure.
I mean, from asymmetry, if you have a denominator dominated by beta Heidler, you will have one-to-one asymmetry to imaginary part, right?
Okay, so the beta Hitler contribution comes in this alpha 1, so it's not multiplied by any GPD.
Yeah.
So those are extra terms, but they are not. They are not beta Hitler.
No. The assumption is in that particular extraction is that you dump everything else, or you actually.
No, we do the full fit of
real
all
parts
those.
as well.
Yeah, so all those alpha terms are calculated. So when we do the fit, we have two unknowns: the imaginary part and the real part.
So you extract also the real.
Yeah. So those error bars with those values are the extraction of the real part immediately. So the thing is, as you pointed out, the alpha 1 factor, and you can see here that the alpha 1 actually, the other factors are prescaled by factor 100 and even 10,000 here. So the alpha 1 factor is very, very strong. And this is the one term that fully comes from beta Hitler, so it's not multiplied by any GPD term. There are some form factors in there, but that's it. And so that's why the real part that somewhat comes like at some kind of correction to it is only contributing as a small contribution that is difficult. And on top of that, they are both kind of cosinus contributions, so it's difficult to differentiate them. But anyway, that's why the error bars are big, is because there is the big beta Hitler in front. But this is the full formula of leading order, leading twists. There is no caveat.
To be fair, this formula is correct only if you have infinitely small b, right?
Well,
because otherwise we will have an integration of propagators which will give you.
That's true of any fit of any
No.
of any data.
This particular one is specifically sensitive to that because you have in the cross section the propagator part which is changing rapidly, and you integrate in a big beam. So the formula, I mean, your extraction of a real part, I think it will be much safer if you just dump that and claim the imaginary part only. With the assumption that the Heidler totally dominates.
There is, I don't see where you see what you're talking about. No, I mean this.
It's what actually the results show. They are basically compatible.
Because there is no sensitivity.
Yeah, there is no sensitivity.
Because you are less sensitive. I mean, you have to look at the size of the error bar.
But if you will take into account the fact that in nominator and denominator, you integrate the propagators with the different kinematic variables, so they don't really cancel. This formula is approximate. It's not a precise formula. And then your real part will be completely irrelevant. So whatever you show
that's
there,
what-
it's like it's normal that you don't have sensitivity, but even that measurement, I think will be very questionable.
Okay, we can discuss more in detail of those fits, but anyway, one thing I wanted to go from, because following this point about having an easy fit and going back to the proton situation a little bit, one might ask, is this proton situation actually tractable? You can see here the different observables and what are the dominant terms in there that you can extract. So you have imaginary part of H, imaginary part of H tilde. For example, the part with E is never leading. So it's always a subleading contribution with E. So extracting the E contribution will be very, very difficult. And one of the methods that people want to use is to use neutron targets, because you see that there are F2 and F1 terms in there, and so you can kill some of those terms by going with the neutron. But of course, when you do that, you have to assume some kind of symmetry and so on, and usually you do that on the deuterium. So what happens with the nuclear effects and so on, and I show that nuclear effects in equivalent are actually big, so that's an issue. And there are another question, which is next to leading order and higher twist. And recently there was a publication of those data, and I won't go into the debate about those data, which is very complicated, but what they're arguing is you can describe those data, those whole A data, using those either next to leading order and higher twist. The thing is, when you do that, eventually you get more GPDs. And so then it starts to be a complicated business. And one of the points I wanted to make is, can we actually check these things using nuclei? Is it actually maybe easier to check that there is an effect or not of this higher twist using a nuclei? Because if you have a good measurement on helium-4, you have a full constraint of everything. So when you start to have different observables, you can actually make a statement about the coherence of those observables and the size of those higher twist and next to leading order effects. So actually going to the incoherent and connecting a little bit with what I was saying with the neutron on the out of the deuterium, let me make it short. So here the measurement is not very much difficult than doing it on the proton. You just put a nuclear target and you measure the same final state as when DVCS on the proton. And what we observe here, you can see here a ratio of the asymmetry we get in the incoherent, so when we hit the nuclei, compared to the free proton. And what you see is that here the asymmetry is actually highly suppressed. It's actually suppressed by about 30%. So this is as a function of T. And this is actually completely unexpected. You see all the models were actually either very close to 1 or even above. So that's a very, very surprising result. One of the questions is this an effect from the initial state, or is it due to final state interaction? And because this is incoherent, final state interaction is always possible. And on top of that, now the observable is an asymmetry, so the effect of final state interaction in this case is not well known. So there are some theory effort now to try to progress on that, and but that's a very interesting. However, it raises a big question, because if the effect is already 30% on helium-4, when you want to extract the neutron from the deuterium doing DVCS, you might be left with systematic errors due to those nuclear effects of the size of more than 10%. That's
This asymmetry is coming from interference between DVCS or...
Yeah, so this is just the sinus contribution to the asymmetry. So we look at the asymmetry at 90 degrees.
So why actually this research would go on?
Well, you're looking at two protons. One is bound, the other is not. If there is no nuclear effect, you want one. And people that try to calculate nuclear effects have said that either nuclear effects are very small. You see the black line is one model from Guzet and collaborators, and you can see the two colored lines are from calculation from Liuti. and collaborators, and in their case, they were saying the exact opposite, that the asymmetry would be bigger.
But as you mentioned, that DVCS amplitude for Nucleus is different. You know, I mean, this is.
Well, in this case, it's incoherent, so
I know
it's.
also have.
So in incoherent, you want something should be pretty similar to the normal proton.
Do you measure the proton?
Yeah, we detect the proton. Yeah.
Measure the gamma proton.
Yeah, so actually here we compare to the previous Hermes point. So their point is actually a mix of proton and neutrons because they didn't detect, but in our case we detect. So we know it's a proton. It's around the G.
You still will have fine-state reactions.
Of course. So one of the things we proposed for the 12 GeV is to actually do tagging. So we detect the remnants of the nuclei to control final state interaction.
No, it's still because your handbag diagram could be any of the proton, right?
Yeah. So you have
the beta hadron is only coming from electron.
Yeah, but that doesn't. Okay, I mean.
Maybe I was confused.
Okay, so just about TMDs, I'm not going to talk about that long. We heard a lot about it. Just to say something about nuclear TMDs rapidly to wrap up. Here there is no experimental data in electron scattering. There are a few things that start to come out in proton and in proton-lead deuterium gold and things like that. But I think the physics case is very similar to the GPDs. If you can say something about the transverse momentum of your modification, it's very interesting. On top of that, people that have done some theory on that actually linked. So we heard about transport coefficient from Ivan yesterday, and they have linked. So they have looked what transport coefficient, how it would modify the asymmetries. So they look at asymmetries in semi-inclusive in this case, but it's very similar to what we've seen, and they see that when you have a transport coefficient, it actually quench the size of the asymmetry. And so you can actually get an independent measurement of the transport coefficient, which, as even mentioned, is actually linked to saturation. So these are different angles you measure, but just to make it short, what happens is now if you measure the sinus and the cosinus moments of your semi-inclusive, you get two new measurements of your transport coefficient. And in the past, we already had two measurements, the absorption that Ivan talked plenty about yesterday. And one thing I pointed at the end of his talk, he didn't compare his data to actual transverse momentum measurement, because that's actually a way to measure transport coefficient. And that using TMDs would have two extra independent measurements of the transverse momentum of the transport coefficient. And for this transport coefficient that, as he said, is very controversial, and at this point you have a factor 10 or more difference between models. In that case, we would have 4 independent measurements of this, so that would be a very nice thing to actually pin down what transport coefficient is. And okay, he mentioned it really fast, but one thing is you can actually connect this transport coefficient to the saturation scale very easily. Some argue it's exactly the same thing. And what I want to point out is that then you can do a dependence measurement of the saturation scale. There are strong predictions for that, and this is somewhere with TMDs where you could actually access this directly and try to say, do I see this A dependence of the saturation scale properly as expected? Yeah, so I'll jump over that, but it's a little bit more argument about doing these things with nuclei that have spin 0, in which case you have only 4 linear functions, which is beautiful. So in the short term, there will be a lot of stuff happening in class 12. The Electron group has been approved to measure nuclear DVCS. in this case, the incoherent tagged. We are discussing more and more with Arut and others about the nuclear TMDs in class 12. We actually a letter of intent he showed before, and hopefully this will go back. In EIC, some of those measurements actually get simpler because of the colliding things. In particular, when you want to go to polarized like nuclei, it's much easier to get those polarized like nuclei in a collider setting, and it's then even more easy to detect them. So that's nice. Also, the higher energy doesn't hurt. And so at the end, this will develop into, I think, in EIC, a whole program of light nuclei, and then moving on to heavy nuclei for some of those measurements. So since I'm over time and we are going on to a discussion on GPDs, I think I don't need to make a summary, but just to say that measurements are starting to come out for these things, so we can start to really discuss real things, and I think that's a very good introduction to what will come with the EIC. Thank you.
Questions? Just first make a comment on your previous slide, where we're also looking into this in solid. First, we have in 3 or even polarized. We're also looking to other ones. We try to think of incremental, maybe a recoil detector there.
Yeah, the problem is to do a recoil detection on a polarized target is pretty challenging. And the Hermes experience, I think, shows that you have to be very careful about not detecting your nuclei. You can say very little.
And we're also looking towards unpolarized heavy nuclei.
Yeah. So then there is all the discussion about this incoherent in principle could be done for any nuclei. It's actually pretty easy. In class 12, we have data that is approved on nuclei. Nobody said let's measure DVCS, but I think it's something that we should move with to have first measurements, because the A dependence of this effect is actually pretty interesting if we want to understand where it comes from.
Okay, yeah, so in the case of Helium 4, you can measure the constant form factor reliability.
The content form factor, what?
Reliability.
Yeah.
So from that you can extract the GPD.
Well, so to go from the content form factor to the GPD, you have a problem, is you don't know the X dependence. So either you rely on a model, so you say, okay, the shape, I just make sure that it's consistent with what I measure, but the other option is to start to use other measurements, and so you can this is not published, but we can actually get like pi0 exclusive production and things like that, so that would give access to other aspects. But if you want to do a full experiment to model independently, get the full GPD, that would be much more complicated. But it's actually a problem that is unresolved even for the Proton. People are proposing double DVCS, but it's actually an experimental nightmare.
This ideal situation is very different.
Oh, the double DVCS in that would be impossible. I mean, on Helium 4 is insane.
So I guess some speculative questions / comments. There are nuclei with spin 3 halves, 7 halves, I say, right? Even maybe 9 halves.
Sure.
That's a ton of stuff to measure.
Okay, so I mean, this is delving in stuff that the nuclear physics, the low energy nuclear physics, has been working on for a long time. The thing is, if you want, so if you go, what's very interesting when you try to look at the shape of hadrons is that higher is the spin, more access you have to the shape. Because when you're measuring the spin half, it doesn't matter what the shape is. You have only access to like a spherical thing. You cannot see anything that is not spherical. It doesn't mean that the object is spherical. It just means that all our observables are blind to these different shapes. When you go higher in spin, you actually start to have access to the spear shape and donut shape or whatever, and that only gets access with higher spin. But for heavy nuclei, I think people in the low energy community have been doing that for a long time, looking at all those different shapes of nuclei and things like that. And I don't know if there is a big plus to do it in terms of GPD rather than doing it in terms of nucleons. The one exception to that is the deuterium, which is, as we know, has a very strange features, and you really need to take into account, even though the binding is so small compared to the mass of the proton and the neutron, you need to go into relativistic effects and things like that. You need to have a very careful description of the deuterium if you just want to describe the form factors. So it could be interesting to go deeper with GPDs on the deuterium to try to understand this better. And this obviously is a very nice object to look at the nucleon-nucleon interaction. But yeah, I think this is the limit of going to higher spin. I'm not sure I see an interest to go at 7 higher than spin 1.
Yes, Andreas?
You briefly mentioned this double peak DVCS to solve this convolution problem. What's the status actually? You said it's a nightmare. But does it mean that nothing will come out? Or?
So, I mean, there was some propositions that were made for JLab. I think the status right now is either nothing will be done. That's a possibility. And if something happens, we'll have a few points. So they will be good just to, if you have a model, you will make sure that they go through those few points at this specific kinematic. And that will have to be enough to validate your model. You won't be able to measure the full X dependence everywhere in psi and T. So you'll have few points where there is a lot of statistics. I mean, where there is slightly more statistics, because it will never be a lot for double DVCS. So that's more or less the proposition that is made right now, is to try to have a few points so that you can have a constraint for models, but it won't go much beyond that.
How big will be the meaning for these 2 points?
Well, people are working on specifics and trying to come with reasonable proposals so that actually it constrains something, and it's just putting points with UJL bars that actually constrain nothing. But it's
can give you some more detail. We have there is one proposal at the letter maintenance class. I'm talking about other one with solid. We try to do, one is a letter intent with exactly without adding any new money, just use the existing approved experiment. That one we will get probably 4 data points with error bar, not too strong, too good. And then we have the other one, which will take a little bit more money, is add a mirror detector outside our solid. So that one we will be able to do one other magnitude data. So we have a lot of data, not just actual data points. If we can, but this will cost a few more million dollars. So we probably don't want to do it without sort of baseline or improved.
Are we? He was. I think you were too optimistic when you said that in Nucleus, incoherent, and the proton is the same detection for DVCS. It's not exactly true in the sense that we have to detect all 3 particles. In addition, you should have enough resolution because to provide exclusivity cuts. You detect 3, and then you also check that photon, for example, is exactly in the direction of the photon where it is supposed to be. But it's not even enough to detect all 3. Now, if you don't detect 3, then you have this luxury of doing analysis of Hermes type or something, missing masses, and then you have a lot of mess there. So if you want to do something precision, you have to detect all 3. Now, additional complications coming from Nucleus is that you have the proton is not really at rest. And that gives you additional smearing that introduces additional problems. more complications with pure experimental factors like high-zero backgrounds and things like that. So if I understood, you are trying just to detect the photon, right? Without the backward proton.
We will have some proton elements, but that will be limited. Just can provide this.
Yes, because it's a large
Very
number,
tough.
so it is.
Very tough.
No, I mean, I think the experience with Hermes, because even when Hermes added their barrel detection for the protons, and you just look at the different, it took a very long time to actually get the two data set to match. I remember at the time the discussions on that, and it's
Probably can conventional physical detector, but this is probably not the best.
No. I think actually it's a very good example that it's not so straightforward about it's what you just said, but even on proton target, it's not so straightforward to just get rid of the proton detection and just assume everything will work fine.
So
those two measurements are actually pretty different. Yeah, it's much better if you did measure the proton. Much better. You have much more control.
It also depends on the resolution. Like our first DVCS experiment, we did both male recoil, without recoil, and turn out without recoil they're consistent, and the proton measurement turned out to be not that useful.
Look, I will.
They had like really good resolution.
Yeah,
right?
yeah, we had very good resolution.
I will go in. I will go in a very contentious place and tell you that you see those data from OA that I seen the last fit Hervé Moutard and collaborators published a fit recently, and they have to exclude those data because they are 8 sigma away. They have a chi-square of 8 per degrees of freedom. So they have to exclude those data. And people are arguing that maybe it's because you... one thing I like to point out is that, well, hey, doesn't detect the proton. And we know that can raise two issues. And the argument is we have great resolution, so it doesn't matter. But the truth is, of DVCS at the end, you detect the photon. And you will never have great resolution on the photon. So that's a problem that you can't get rid of. All the lessons and beyond Hermes and all this OA stuff, to me means doing DVCS without detecting the fact that you have this intact thing at the end is a dangerous thing to do. If you have any chance to measure it, and not measuring it is going into a dangerous place.
Nucleus,
No, I mean, this is proton. This is proton.
I'm not sure I agree with you. With the first experiment, they had completely checked. They totally agree with and without proton recoil.
Well, then why is it that? I mean, the
whole
A data is a very good example that actually.
I can share you the comparison here.
From which experiment?
From the first Hole experiment.
No, but Hole never detected properly the proton.
We did. The first one did very okay.
Very well.
Okay, I'm a little bit different. Different situation, and because also in the TMD case we were kind of so the statement was that if it's pity that the other speaker is not here. We were supposed to speak about that.
Which other? We're supposed to have two other speakers.
Jan or
Yes. Because they came up with the idea that you actually modify the orbital motion. So you modify orbital motion. In a sense, you have wider distributions. And I'm not sure, because Simonetta was making those, her GPDs had different BT distributions, right? So, you look just in the final prediction, but that corresponds to BT distribution being wider, for example. in the medium. So it's kind of natural to expect that in fact transverse degrees of freedom are the ones that are modified in medium, and everything else is the reflection of that.
You're saying larger nucleus has a steeper T-slope.
Yeah, like you
Just
put
because the radius is
quarks together, all the orbital motion is different than it was before when it was a single proton. That was the point. In fact, it was supposed to get, and that will, if it is orbital motion, then it depends on the spin. So different spin states will modify in a different way and things like that. So there are a bunch of effects that were around that can give a hint how the orbital motion of quarks is changing in the medium. Part of it is the transverse space distributions modification. Part is transverse momentum modification. So so far theory didn't really make any strong statements about that. And I mean, it's natural to expect that if you change all your PTs, let's say, and you detect hadrons in the final state, you will obviously affect all kinds of your distributions, including the longitudinal degrees of freedom. So all that correlations of transverse and longitudinal comes here in kind of more obvious way. That so far our communities were completely disconnected. So on the same people doing both, they never link anything they do for one dimension with anything they do in the other dimension. But they should be kind of connected, right?
I agree with you. I mean, this is, if you have like all those models that go with nucleon swelling and things like that, even if you just if you think if you start to go at low X, the nucleons get bigger and you have a lot of overlap between nucleons. So this has to have an impact, especially, but I think here for those measurements, the cleaner is probably to go TMDs, because the GPD part.
It's strange that you are such a GPD guy.
No, but,
and I like actually the modification of the transfer space distributions.
I want to understand the nuclear effects. I'm not defending GPDs against TMDs. I'm not in this business of fighting and housing.
But it should not be exchanged between me and you that you like more TMD modification. I like GPD modification, but our theories should kind of give a
what I'm saying,
how that is.
What I was getting to is that so the problem with DVCS right now is that in DVCS you're an exclusive process in principle, and so when you start to do an incoherent exclusive process, it's can start to be a little bit messy. So the hope is that tagging will resolve that. So that's something that is proposed, but until we actually measure it and confirm it works, I mean. Up to now, when we measured tagging, it worked differently. I mean, that was not the topic of today, but until this is proven, the fact that TMD works based on semi-inclusive, if you want to do nuclei, and especially, I mean, at the end, I talked only about light nuclei, but if you want to do TMDs, you can go to any nuclei very easily, because now the final state interaction is part of the TMDs anyway. So that's there is no problem of the coherence of your theory. Everything works together very nicely. So I think for the GPDs of nuclei to go to work in the incoherent, the coherent part works beautifully. I think it's very nice. But the incoherent part, so to get to what you were talking about, we have to prove that tagging works before we can say anything.
So,
okay. Are we in
sorry, maybe orbital motion should be there.
I think it's discussion. This is a discussion mode.
Oh, yeah, we kind of discussed, right?
This is a discussion because you guys are the leaders, Arut and
Okay, you just have to translate yourself.
All right, okay.
Yeah, can you go back to the helium-4 plots of
the what
theory compared with the data? The helium-4.
The coherent?
Incoherent.
Incoherent.
Yeah, I guess maybe the question to you and also to the theorist. This model, helium-4 has very strong nuclear effect. It's a very strong bond. but the effect is small. Maybe it's because it's around X, around 0.2, where the inclusive EMC effect is small, and then they just use inclusive as kind of a constraint to give you a small effect. But the data is telling you, even at 0.2 around there, the EMC effect is very strong.
I mean, nobody knows what this is, but the data point is at 0.27 average Bjorken. So if you remember the distribution, this is more or less where it crosses 1. So on the nuclear PDFs, this is a place where you have very little modification. Now you can, you are at the transition between anti-shadowing and EMC effect. So the fact that it crosses 1 doesn't mean there is no nuclear effect. It can be the cancellation of 2 effects, and if they are not localized in the same place, then in the GPD you can have a huge nuclear effect. I mean, the theory here is really at the starting point. I mean, I don't want to go in details in the theory models. Don't really have the slide, and I didn't go back to them for a while. So,
and my point is that with this initial data already indicate we need more theory.
That's the hope. My hope is that with those data coming out, and we should have the validation from the collaboration any day. So it could be on archive in a few weeks. So this should come out, and I hope that the theory side will start to look at these things. I know there are plenty of people that have models that can actually describe these things, but they have to process a little bit for these specific observables.
Okay, any other comments? So, all right.
Andreas, you don't want to say anything? You were telling us that the beginners are the place where we finally can handle the whole orbital motion altogether. And it merges our TMD and GPD interests.
Yeah, that could be. I mean, I never worked in nuclear, so be careful to say anything.
Such as big problems.
Well, one of the interests of working on the coherent process is that this is just a spin zero.
Yeah.
We don't. I mean, if you want to model it, then you have to do some nuclear physics. But if you just want to, you can have a look that is completely independent and say, I'm just looking at a spin zero atom. And if everything is coherent, this is the same thing at the start and the end, then, from the purely theoretical point of view, it works nicely. And at the same time, I mean, for example, people who have done the spin zero to actually not for nuclei, but at the start it was to look at pions. And you could argue that it's exactly the same in terms of the theory. Then at the end, of course, the functional style could be very different.
Okay, it occurred to me that we don't have any theorists at present who actually thought about this. I'm not sure we can have a very, I mean, you can ask, you can put Andreas on the spot and ask him to describe this data on the spot, but it's not.
But the data, one thing I didn't show, the data on the coherence, there is a paper from Scopetta that came a few months ago. He was here during the first week of the program, and he showed the results, and they described the data very nicely. So they have a model. And, I think one of the main issues for them is to try to get models of the nucleus that are covariant, because the DVCS framework, of course, starts to have issues when it's not. And so they're working very hard on that.
I mean, the one point which you emphasized, which I do find interesting, even though I don't know how reliable the theory is, to look at TMDs and to get access to this transport parameter. I mean, that's really, I mean, to the extent that the theory behind this is solid or semi-solid, I think this is a,
I think it's very
this should be done.
It's very clean because there is one simple reason why it's very clean, is that all those asymmetries, they show up at the Parton level. And so you're completely, there is no sinus asymmetry that shows up in the fragmentation, things like that. And if you go to EIC, all the fragmentation is outside of the nucleus anyway, so it cancels out completely when you do ratios. So those are pretty clean. Now, a work that has not been done, we've been discussing, and I think there is a little bit of progress to do, and it could be very interesting, is to start to separate what are the contributions that are, because some of the modulations are purely initial state, and some will be mostly final state. And so looking at that should be very, very helpful to also separate other effects, like what Ruth was talking about, if you want to start to see how much the transverse momentum is modified when you put the nucleon inside the nucleus. So that would start to look at all the different modulations and say which one is sensitive to what. And that's a little bit deeper to look at. But in general, at the first order, the first contribution you will get is always the transport coefficient. And that's relatively clean. There's very little doubt about that.
So, but I want back to proton phase again. So, I mean, GPD was proposed like 20 years ago as one of the problems in China to really get a hand on all the angles. Have you guys thought about that?
To get to the orbital angular momentum?
Yeah.
But through E, you mean?
Yes.
Yeah, the problem is to measure E.
Yeah. I mean, you mentioned about how difficult.
So actually, the nucleus is interesting for that, because if you
I really want to get a proton.
Yeah, but actually that connects to if you look at this diagram, when you're in this diagram, if you think that nuclear, you look at this nuclear DVCS in terms of this diagram, so what you get are contributions from GPDs of the nucleon, right? Because you're hitting a nucleon inside the nucleus. And as it happens, because the spin 0 at the start and the end, you cannot have spin exchange. And so it kills the H tilde and E tilde. So the H GPD in that case is actually the sum of H and E in the nucleon. So maybe there are some hope to get some things. But right now, the best hope that people are looking at is to measure the neutron to get access to E. And as I said, the problem is right now the most recent lesson we got from doing incoherent measurements on nuclei is that you have a very big modification. So that raises question on how precise can you get, because people will extract 1% uncertainty on the asymmetries for the neutron out of the deuterium. And then what we are showing is that actually you might have a huge effect, huge nuclear effect.
But that modification made, I don't know, I actually meant to ask it. So when you look at T very small, actually modification somehow is not that much.
Well, it's, I mean, within our bars, it's constant everywhere. I mean, it's.
I mean, particularly if you integrate T, I think that.
I mean, within our bars, these guys are the same, but even the smallest T is like that's 0.75. So
yeah,
25% modification in the gum is.
Your error still.
Wow.
Yeah, so that means
you have 3 points that are more than the 2.
My comment is for it. So when you go to T equals 0, maybe modification is not that strong.
Maybe.
So they wanted to say actually the nuclear modification could come in from because now you have a single spin asymmetry there. So the nucleon response.
Let's be clear, what you're saying would be actually worse.
Yeah.
Because that would introduce a slope.
That's fine because you only enter the T equals 0.
But you're looking at the extrapolation at T equals 0. So if you introduce a slope and now you you extrapolate, that means you're extrapolating.
No, you don't. Place. I mean, you just push as small as possible T, and so you don't have to.
You can't. You have a T.
Yeah, I know.
But just even if I think we will be able to get E one way or the other, but you always have limitation. What he made is that Psi equals X.
That's
You
true.
need to integrate all.
I mean,
for
we
X.
know
That's
that.
impossible.
We know that. You always have model dependence. That can be considered as part of the stability uncertainty, right?
But
It's not just model dependent.
it's not a small
Go from one
numbers,
point
but
to get infinite integrations.
if you put yourself
can only
and
use small.
looking
So,
at
I don't know. I mean, is that consensus now from GPD community? We cannot really get all them.
Oh yeah.
no,
We,
that's
a
not
few
true.
years ago, we were holding all these discussions.
But I say I understand that there will be model dependence. But if the model dependence is
But it's like we've seen some figures of people showing delta G, and they say, okay, it's an integral between 10 minus 3 and point something. I mean, it will always be like that, and any of those measurements will always have some limit. But if you put together a program of GELAT12 that will go pretty high in X to a program at EIC that will go pretty low, I think at the end, you will have a pretty good picture of E if you can actually get the handle of all those caveats on how to extract E. But I mean, you will, if you put together those two, you will have measurements that is very reasonable between 10 to the minus 3 and
But even you have all this,
1.5 or
you're not
something.
at constant Psi. You're at Psi equal X. You're on this ridge. The integration is not here. So this is totally two different.
I agree.
Once you have a model, I mean now already
You need a model.
existing extraction from the data people were calculating orbital angular momentum, right? You have a model, you bring it to 0, you calculate your sum rule, and you get your orbital angular momentum. Those exercises people were doing last 10 years.
You have two ridge. One is forward ridge, one is actually Psi ridge. These are the two lines you will know. Then you try to get your two-dimensional, even independent of T, assume T, you can take T for 0 limit. You have two-dimensional X and Psi. You can get one from your forward and one from DVCS from X equal to Psi.
So
The two line you get.
so let me just get to the point. So I think last time we also talked about this, and in the end we didn't emphasize too much on the speed summary. So I think from what you guys were saying, that maybe we just finally drop that part.
No. What I'm saying is eventually you get it.
Yeah. I mean, there's no.
You have to drop, but this topic cannot be the super and only goal of the community. That was at some point it was like put on the flag, but it is obviously is not something that you have to keep it there. I mean, it's one of the things that you can do.
The flag.
Certainly, it's not something that should be the main focus of the community.
It's not a shining slide.
No. Yes,
But
So
if
we
you
should put Shandong here. Okay.
You need a double DVCS to go off that ridge.
That's true. I know. It's a very good.
But all those measurements, I mean, and this is not a critic about GPDs or about anything. I mean, all of them, there is always at some point some model dependence about one thing or another, or how many we talked about the jet side production and the fact, okay, now you start to do